2.4 Recurrence Relations for Arithmetic and Geometric Sequences. Our learning intention, how to find recurrence relation for arithmetic and geometric sequences. Success criteria, I can find recurrence relation for given sequence. I can develop a general rule from a sequence to find the nth term for both arithmetic and geometric sequences. Sounds like a mouthful, but it's not really. We'll go through this. So far we have learnt about geometric and arithmetic sequences. Remembering with arithmetic, we need our initial term, A, and we need our common difference, D. After that, you can find any number in a sequence. So, recurrence relations for arithmetic sequences. Since an arithmetic sequence is formed by adding or subtracting a constant number to each preceding term, the recurrence relation for an arithmetic sequence is T of 1 equals A, we know what our A value is, and T of n plus 1 equals T of n plus D, where D is the common difference and A is the first term. We also know our common difference and how to find it. So for worked example 7, which is on page 278, let's pop that down there, oops, page 278 of your textbook, find a recurrence relation that generates the arithmetic sequence 30, 27, 24. Remembering all we want to find in this case is our A value, our D value, and then plug it into a formula. So let's start with our first term. 30, 27, 24. As we can see, our first term or our first number is 30. So that is my A or my T1 value. My common difference D is using the formula to find my D value. T2 minus T1 equals 27 take away 30, giving me negative 3. Step 3, write the recurrence relation. Now all I'm doing is I'm taking this formula and I am then plugging in my A and D values. So T1 equals A, from step 1 we found that to be 30. And then T of n plus 1 equals T of n plus D. But in this case, our D is negative, so we do minus 3. It's using the same formula at the top of the page highlighted in green and just plugging in our A and D values for this sequence. So using a rule for arithmetic sequence recurrence relations, we can use a CAS calculator to generate arithmetic sequences through recursive computation as shown on page 271, or we can apply the rule T of n is equal to A plus n minus 1 D. Now if you're after CAS instructions, I've created another video called CAS instructions for arithmetic and geometric sequences. Use it, watch it, learn it. It becomes invaluable, and once you have learnt it, you really can't forget how to use your CAS. So, worked example 8 on page 278 of your text. An arithmetic sequence is defined by the recurrence relation T of 1 equals 4, T of n plus 1 equals T of n minus 8. Now, remembering this rule from before, previous slide, equals A, T of n plus 1 equals T of n plus D. That was the recurrence relation we used. Now we need to find a rule for the nth term of the sequence. We need to find all of our values. We want to plug those values then into this formula and simplify. So that we then have, all we need to do is put in an n value and we can find our T of n value. So a little bit of rearranging, a little bit of expanding a bracket, nothing you haven't seen previously. At least nothing you haven't seen in previous years of maths. So I'll take the formula above, T of n equals A plus n minus 1 D. In this case, my A value and my D value are, there we go, 4 and negative 8 respectively. So what I'm going to do is I'm going to substitute them into my formula. So T of n equals 4 plus n minus 1 times negative 8. We'll rearrange that formula. T of n equals 4 minus 8 outside of n minus 1. Now comes the tricky bit. You need to expand the formula. From that, you can then simplify. All right. 4 minus 8 times n is 8n. And negative 8 times negative 1 equals positive 8, because you've got two negatives there, equals 1 positive. So negative 8 times negative 1 equals positive 8. Then we simplify again. So 4 plus 8 is 12 minus 8n. So if I wanted to find the 10th term, I just put 10 where n is, and that would give me the 10th term. If I wanted to find the 48th term, I just put 48 where n is, and I find the 48th term. So part B of this says find the 12th term using this rule. So all I'm going to substitute in is T of n equals 12 minus 8n. I want my n to equal 12. So I want my 12th term. I do T of 12 equals 12 minus 8 times 12. And 12 minus 8 times 12, little side note, is 96. 12 minus 96, keep putting T of 12 down the side, equals negative 84. So my 12th term in the sequence would be negative 84 if I continued down by 3 each step. Sorry, by 8 each step. All right, moving on to geometric. Recurrence relations for geometric sequences. So remembering with geometric, we needed our initial term and we needed our common ratio. So since a geometric sequence is formed by multiplying the preceding term by a constant number, the recurrence relation for a geometric sequence is T of 1 equals A, T of n plus 1 equals R T of n, where R is the common ratio and A is the first term. Okay. Cool. We're going to go back to green because green looks better. We need that formula soon. Until then, we've got to work through worked example 9 on page 279. So, find a recurrence relation. This is the recurrence relation in the green, highlighted in the green again. Find a recurrence relation that generates the geometric sequence 72, 36, 18, 9. So write down the first term. This is my A value. So I've got my T1 or my A value, and my first number is 72. Then my common ratio, my R value. I know that my R value is my second term divided by my first term. In this case is 36 on 72 equals 1/2. All I do from there on in is substitute. Using the formula at the top, T1 equals A, and my A value is 72. T of n plus 1 equals 1/2 times T of n. Meaning all we're doing is we're starting off with the number 72, and every number thereafter we're just halving. So 72 times 1/2 gives you 36, times 1/2 gives you 18, times 1/2 would give you 9, times it by another half, you'd end up with 4.5, 2.25, and so on and so forth. Using a general rule for geometric sequence recurrence relations. We can use a CAS to generate geometric sequences through recursive computation. Again, in the video, have another look at it later if you need to, as shown on page 271. Or we can apply the rule T of n equals A R n to the power of n minus 1. All right, that rule again. T of n is equal to A times R to the power of n minus 1. All right, work example 10. We're on page 279 of your text, if anyone's following from the textbook. So, first of all, we need to find the rule for the nth term of the sequence. the first thing I need to do is find my A value. And I know my T1 is equal to my A value, which in this case is 4. And my common ratio, pull my pink highlighter again. Oops, wrong one. My pink highlighter there, they're the two numbers I need. So my A value is 4, my R value is 0.25 or a quarter. I then take the green rule above, substitute these values and get myself an answer, or I get myself a rule. So, T of n is equal to A times R to the n minus 1. Let's substitute in my R, which is 4, and my 0.25 to the n minus 1. I'm going to put that in brackets so you can see that 0.25 is all to the power of, and that is my answer. Didn't need to simplify like I did with arithmetic. And I've got, all I need to do is I need to change or put in a new R value, and this will then give me the term that I'm after. All right, so find the fifth term using this rule. Let's use the formula. T of n equals 4 times 0.25 n to the 1. That's my T of n. I want the fifth term, so I put in T of 5. 4 by 0.25, 5 take 1, 2, 5, to the power of 4. All right, let's pull up a calculator. 0.25, let's see if I can figure this out. The power of 4 gives me a pretty small number. Then I'm going to times that by 4 and get an answer. All right. 0.0390625. So it's 4 by 0.003, back to that number, 90625. 90625, multiplying them together, and I get 0.015625. Now it doesn't actually ask me how many, or doesn't specify how many decimal places I need. So in order to get a number, I put in as many as I can. So taken directly from your textbook, I have put in question 3. It's got all the multi-choice answers, but I'm just going to go through this step by step to show you how to find the solution based on the recurrence relation that you've got. So we have our recurrence relation up the top here. We need to pull out our key information. T1 equals A equals 20. And we know that the rule for the nth term is T of n equals ARn minus 1. So I've got 20 as my A value. So looking through each of these, I've got 0.2, no, 0.2, no, negative 20, no, negative 20, no. So I should end up with E. Process of elimination, but I still want to double check. And this value over here is my R value. R equals 0.2. So if I substituted it back into this formula, I'd have T of n equals 20 times 0.2 n to the minus 1. Yep, it's E. And question 4, again, taken directly from your textbook. We're doing the same, or using the same concept, but we're trying to find an arithmetic sequence. Neither sequence is actually specified whether it's geometric or if it is arithmetic, but you'll note by the operation in the middle of it all whether it's geometric or arithmetic. Remember, arithmetic is plus and minus, geometric is multiplication and division. All right, so using this formula here and using this formula down here, t of n, well, let's try and write neatly. T of n equals a plus n minus 1d. We need to do a bit of simplifying. All right, t of 1 equals 8 equals my a value. My d value is this plus 5 at the end. So now I need to try and substitute in. Let's go. 8, t of n equals 8 plus n minus 1, 5. Rearrange it so it's a little bit neater for me. And we expand. 5 times n is 5n. 5 times negative 1 is negative 5. 8 take 5 is 3. We've got 5n left over. What have we got left? So I've got 3 plus 5n, or 5n plus 3. That should mean it is A. All right, that's it for 6.4. Thank you.